Okay, so I want to think about eigen values for a matrix raised to a power and a matrix's inverse. Please note, need not exist. Right? I have an arbitrary matrix A. It doesn't necessarily have an inverse.
But it might. It could.
Yeah, so let's talk about when it has an inverse for one thing. So when does A have an inverse?
And the determinant is non-zero.
Okay, so that's good. When the determinant of A is not zero. I suppose I should probably just put an n by n up there. We're talking about eigenpairs, right? Like, this is all in the context of eigenvalues. Eigenvalues aren't defined for not square matrices. Why not? For one thing, you can't invert a rectangular matrix, so that's why would I not be answering this question about inverses, right? Yeah, kind of one of the ways that I lay my hands on eigenvalues, right, is I take the determinant of A minus lambda I. Probably not even going to figure out what I is in the not rectangle or in the not square case. Furthermore, the thing that characterizes an eigenvector, right, is that A takes x to lambda x, where lambda is a scalar, right? This isn't going to work if A takes x, like if A takes vectors in Rn to vectors in Rm, because this statement doesn't make any sense.
Oh, because x won't be the same dimension.
Yeah. Right, x certainly won't be a scalar times itself as if this thing takes it to a different dimension.
Oops.
You see that? So these are only going to be defined in rectangular or in square matrix land anyway. So square matrix land. When does A have an inverse? Well, when the determinant's not zero, right? Great. How about phrase that in terms of eigenvalues?
So, if it's already zero, like if the determinant's already zero, then there's no point of trying to find where A minus something is also zero.
Oh, but there is, because we did that. Like,
Yeah.
I think I might even have it right here.
Oh, dang.
This matrix was singular, right? Like, straight up. Definitely doesn't have an inverse because it's the zero matrix, but I was able to produce some eigenpairs. When I'm calculating eigenvalues, right? The way I do that is I take the determinant of A minus lambda I, right?
Mm-hmm. So in this case, it would be A to the K minus lambda.
You see this kind of weirdness here? What if I thought about A as A minus 0I?
Okay.
I mean, it's not changing anything.
But that would say lambda 0.
Yeah, so if the matrix were singular, right, then its determinant would be 0. And so 0 would be one of its eigenvalues?
Yep.
You guys see that?
So,
So,
I was going to say it needs to have eigenvalues not equal to 0.
yeah.
So lambda not.
You guys see that? So when does A have an inverse? Well, when the determinant of A is 0, is not 0, or when 0 is not 1 one of A's eigenvalues.
Also, there was something that I wanted to mention, just as a
Just say it louder so the camera
okay,
can get
just
you.
as a guess, what I did for this is that if you have two eigenpairs for matrix A, for A inverse, I'm guessing that they're going to be the same, so the eigenvalues are going to be the reciprocal previous eigenvalues.
That was a really good thought. So, if we're thinking about what A does to stuff, right? So I'm like, okay, so let me suppose that A inverse exists. Right? Now, I'm considering this equation, right? Ax is lambda x. You guys see that?
Yes. X is.
That means I can multiply through by A inverse, right? Because A inverse exists. So that would tell me that x is
Inverse lambda.
A inverse lambda x. And now we have to figure out the categories of everything here. That's a what?
Matrix.
That's a matrix, an n by n one specifically.
Yes.
What's lambda?
A scalar.
It's a scalar. What's x?
A vector.
A vector.
We can do that.
So what can I do with this scalar in the middle?
Move
Pull the
it.
scalar from the matrix and apply it to the side.
Good. You can swap the order, right? Because it's scalar multiplication. So I can swap this to x is lambda A inverse x, right? And then I can divide. But divide by lambda because it's a scalar.
Ha ha.
So 1 over lambda x is A inverse x.
Solid, dude.
Nice.
So that's a little sketch, right? You'd want to write this down a little more carefully to get a proof, right?
That's why 0 can't be a thing.
But this kind of motivates our claim, right? One, I can pretty clearly see that if lambda is 0, I'm going to have a problem formulating this, right? But I can also make a little claim here. And my claim is going to be this. Claim is going to be lambda and x an eigenpair for, pair for A implies what's an eigenpair for A inverse? Fill in this blank.
1 over lambda x.
Yeah.
Perfect. 1 over lambda and the same eigenvector.
That's sick.
Isn't that fucking cool?
Good job.
This is super cool. You guys with me on this?
That makes
And the
like some-
proof for this claim, right, is essentially this little bit of algebra with some justification that I set into a camera, so I'm not going to write it down. You guys good with that?
Yeah.
Okay, so the thing I want you guys to do is think about the A to the K's. You can do this.